before we start, I wanted to kind of, we had, well, a short time where we did not have seminars around here, and as well as this distinguished lecture series was on pulp. And as we now revive it, I looked a bit into the history of how it started and what brought us here, and I learned that today's actually a special occasion for a number of reasons. It turns out that this lecture series was founded precisely a decade ago. So we are now exactly 10 years from the inaugural seminar of this lecture series. It was established in 2012, and if my sources are correct, it was announced at the retirement party of Professor C.C. Mei. And it was endowed by contributions from Professor C.C. Mei's colleagues and friends and students from over the years. And I'm super excited to have Professor C.C. Mei here with us, which makes it an extra special celebration. And what I've learned is that the goal of this seminar series was to bring leading academics to MIT to share their research advancements and their discoveries. And this was in recognition of Professor Mei's boundless intellectual curiosity and his excitements for pursuing knowledge in applied mechanics. And I think our distinguished speaker today embodies that spirit, as we can already see from the title of his talk and from the work that he has done over the years. And I think we've all been really looking forward to this talk and to the revival of this seminar series. And I will hand it over to Hudson to introduce our speaker.
Thank you, Tal. Hi, everyone. So I'm Hudson. I'm a postdoc in a group of Professor Coins. And I have the pleasure to introduce Professor Alain Goriely. And I had the pleasure of being his student back in Oxford. Shortly after receiving his PhD from the University of Brussels, Alain Goriely joined the University of Arizona, where he established a research group within the renowned program of applied mathematics. In 2010, he joined the University of Oxford as the inaugural statutory professor of mathematical modeling, and is also a fellow of the St. Catherine's College. He is currently the director of the Oxford Center for Industrial and Applied Mathematics, and is also the international brain in Mechanics from Lab. He's a mathematician with broad interests in mathematical methods, mechanics, science, and engineering. He is well known for his contributions to fundamental and applied solid mechanics, and in particular for developing a mathematical theory of biological growth, culminating with his seminal monograph, The Mathematics and Mechanics of Biological Growth. In addition, Alain enjoys scientific outreach based on problems connected to his research, including tender perversion in plants, twinning plants, umbilical cord knotting, whip cracking, the shape of seashells, brain modeling, and he's also the author of a very short introduction to applied mathematics. For his multiple contributions to mathematics and sciences, he was elected Fellow of the Royal Society in 2023. Being a great communicator, I'm sure everyone will enjoy this talk today, entitled The Mechanics of Chirality, from Darwin's Perversion to Feynman's Obsession.
Thank you very much, Hudson. It's always a bit of a danger to have a previous student introduce you. You know, they have all the dirt on us, so I escaped on that. Well, thank you very much for the honor of being here today. It's a great pleasure, and I had a wonderful visit. So I will be talking today on the mechanics of chirality, which at first might seem a little bit something that doesn't quite match. Chirality is mostly a geometric notion, and my message today, if there is one, is that mechanics also has an important role to play with this type of ideas. It's a general field, chirality, handedness, and all that, for which I've been a little bit obsessed since I remember being an undergraduate student. And I'll talk about some of the problems that caught my attention back then. And over the years, I've always found myself going back to this problem, trying to understand basic questions. The real problem, the essential real problem is to this day, I don't know if chirality is an extremely deep problem or a completely trivial one. So maybe you'll help me understand or answer that simple question. Nevertheless, being a bit of an addiction, an obsession, if you want, just like others, I was told that one way to deal with that problem is to talk about it. So you should look at it as a therapy session for myself right now. So let me jump right into it. We're going to talk about chiral structure. Let's see, we can start with a simple straight line, a straight curve, that has no tension and no torsion or no curvature. If we add curvature, we can make a ring out of it. So here we have the first notion. You start straight, you make a curvature, you have a ring. These objects are achiral. By opposition, as soon as you have torsion, the torsion here in the case is negative torsion, you can create, if the torsion and curvature are constant, a helix, the basic geometric curves. And if the torsion is positive, you create a right-handed helix versus a left-handed helix. So what is chirality? Chirality is not a property. Chirality is the absence of a property. One says that an object is chiral if there is no rigid body transformation that maps its mirror image to itself. The name was introduced by Kelvin in a lecture in Oxford in 1893, and it's really based on some of the idea that was previously put forward by Pasteur. I'll show you a little bit. So I wanted to put that straight from the get-go because it turns out that 15 to 20% of the population have an issue distinguishing left and right, as you can ask my wife, for instance, when we drive. Having that on the first screen is important. So you see that there is a little moon there. Also, I'll come back to that, and the generic Latin word, sinistrosum, for left and dextrosum for right. So if you want to remember, with your right hand, you can go like that on a helix, and with your left hand, you would go like this. Or you can use the so-called right-hand rule that you might have learned in calculus, in vector calculus. If you put your thumb in the along the axis and turn it, it would follow the helix. Okay, so we have ways. Where does that rule come from? Well, Feynman would tell you that the right-hand rule is merely a convention. It was a trick. And we'll explore a little bit where this trick comes from. Why do we decide that this is right and this is left? So I want to put it in a more global framework, not just looking at object with constant curvature, but in general, let's talk about curves. We can talk about surface and volume in 3D, but let's talk about curves to start. If I have a curve and sufficiently continuous, then I can attach a basis at each point. And I'm going to attach a right orthonormal basis at each point, where the vector D3 is along the tangent. So you define if you have a curve, and it's if you can take it's differentiable, let's assume it's C2, then I can take its derivative, and the tangent vector is a unit vector along that. And I define two vectors in the normal plane that are perpendicular to the tangent vector. So if D1, D2, D3, I can define that at every point, and hence, along the curve, I can write an equation for the change of these vectors along the curve. And since they are at all time a right-handed orthonormal basis, I can write it as a cross product by a vector u, which is the curvature vector. It's often called in geometry the Darboux vector. It's related to the notion that we know, curvature kappa and torsion tau by simple rule. So there are three main objects to define the shape of a curve. If you give me u, I can integrate this equation in principle. That would give me the tangent vector, and I can integrate once more the tangent vector to have the curve. So the fundamental theorem of curve tell you that given curvature and torsion, I can find the curve. Here we have an extra notion, which is particularly important in mechanics, that on top of that we can have a rotation along the curve, which defines what is called the twist. Right? If I have a belt and twist it around, I can have a straight curve with zero curvature and torsion, but with non-zero twist. So we have three quantities that we use to characterize this object. Already, it's not quite completely obvious. There is a very nice paper dating back from the 80s by Feynman and Alexander called The Ambiguous Twist of Love that noticed that twist and torsion and curvature are somewhat intermingled in the curvature, right? And it's a very subtle point that we'll see again that turns out to play an important role in some biological problem. So where do we see chirality in nature? We see it in the gigantic flux tube that comes out of the solar corona, for instance, a gigantic size. But on planet Earth, you'll find it in some construction. I don't think that was ever built, but that was a project in Panama City. You'll find it on trees. You'll find it on twining plants. You'll find it in umbilical cords, two arteries and one vein that wrap around each other, making themselves an overall twisted object that has itself curvature and torsion. And at still smaller size, if I go down, you'll find plenty of seashell with well-defined curvature, like this beautiful striped horn. If I keep going down in size, I can look at plants. Turns out that many roots of plants have twisted roots that have well-defined curvature, and they're a very nice experiment for Arabidopsis. So where does that curvature and torsion come from? Where does that helicity appear? Where it comes from the structure of the cell itself. If you look most closely, you'll see that you have files of cells that twist around the root and that create an intrinsic twist in the system. If you keep looking closer, the cells themselves have a chirality that's inherited from the microstructure, from the placement of the microtubule around the cell wall. Right? So each level of chirality, the fact that you have a right-handed structure at different level, come from the previous scale. You can go even smaller. If you look at keratin, for instance, one of the many protein assembly, keratin, the basic protein that you have in your hair, or nails and things like that. It's themselves are made of two alpha helices. So if I go down a little deeper, you'll see the alpha helices that have a well-defined right-handed chirality. Why do alpha helices, one of the most common secondary structure in protein, has a well-defined right-handed chirality? That comes itself from the fact that amino acids are found almost exclusively in one hand versus the other one. For instance, this amino acid that you see there is the one that you'll see in all organic chemistry. You will not find its mirror image, which you could create by many synthetic processes, but when it comes to organic life, it will always find one well-defined handedness. Okay, so there are, if you look in different fields, not only in science, but in philosophy, there are many interesting questions related to chirality and handedness. Starting with philosophy, for instance, Immanuel Kant says, what can resemble my hand or my hair and be more equal in all points than its image in the mirror, and yet I cannot put such a hand as is seen in the mirror in the place of its original. So that's related in philosophy to the absolute notion of space, or relative notion of space. And to this day, it's still a very active philosophical field that many people, including people like Einstein, have thought about or tried to give an answer. In the field of physics, this problem of chirality are called parity, and it's related to the fundamental notion of whether or not there is symmetry breaking at a certain level of physics. In this case, it's found at the level of weak interaction in beta decay, for instance. And it's the scientist Qin-Shing Wu, who in 1956 did the fundamental or seminal experiment on cobalt-60 that proved that parity was broken at the level of this interaction. This is the only place in physics where parity is broken, or the first time, the first scale at which it's broken. And as Feynman would say, who also came back to this problem many times, the rule is that the particle which carries spin out in weak decay, with a spin mostly to the left, now that is the rule, but today we do not really understand the whys and wherefores of it. Why is the right rule? What is its fundamental reason for it? And how is it connected to anything else? Feynman would come back many times to this type of problem. In biochemistry, or more generally in biology, there is a question about the ultimate origin of chirality. Why do we have a certain type of amino acid that we find all over the animal world, all over the living world, and not the other type? There is a lot of speculation over the years. It can maybe be due to the weak beta decay. Maybe it's due to the polarized light that you find from a neutron star coming to the Earth. So you can take your pick between 10 to the minus 10 meter or 10 to the 10 meter or plus, the origin of chirality. In biology, the fact that we have a brain that's mostly divided in left and right, with each highly specialized and with very few connections between the two, and the fact that the brain is not fully symmetric is also very important. Many people believe that laterality is very important for the evolution, for instance, of the human brain. In genetics, we still do not know exactly how the handedness, which appears, let's say, 10% of the population around is left-handed, is being carried out systematically from one generation to the next. In psychology, there is an interesting effect of the so-called left-right confusion in psychology, and you can find it, for instance, in many pictures of DNA. I saw some more. I'm very attuned to these things working in the MIT hallways, where you can find left-handed DNA in a few places. And even in an Argentinian banknote, you'll find also a left-handed DNA. There is a form of left-handed DNA, but this one, the most common one, bDNA, is right-handed. It's not that important. We're not that attuned to left and right. We easily miss left and right. There's probably not that much evolutionary pressure to see the difference. But if you go to the doctor and they operate you on the wrong side, it's become quite important. So I'm not a philosopher. I'm not a brilliant theoretical physicist. I can't answer all these grand questions. But I love to look at little questions. So what are the little questions that are related to chirality that are also of interesting? For instance, a simple one is if I empty my bathtub, I'll see a vortex. If I look from the top, is it going to go clockwise or counterclockwise? Any idea? So we were told in part of the new method of teaching is that you have to get the audience, so the student, to interact. So let's try. Let's give a good example. Who thinks it's going to go clockwise? Who thinks it's going to go counterclockwise? Who thinks it's going to go neither? Neither. We have only three possibilities, right? So it's a question that's been looked at here by Asher Shapiro, and probably maybe there's a good story that Professor Mei wants to share with that, who did the experiment here and had a very nice answer about it. And by Trefethen, not the Trefethen who was faculty here, but his father, Lloyd McGregor Trefethen, professor of fluid dynamics at Tufts University, who did the same experiment in the southern hemisphere. So here is another experiment of interest, and this is the one that I first read in Seriously You Joking, Mr. Feynman, a book of Feynman about his life. He talked about an experiment he did in Princeton, and the experiment actually comes from the book of Mach from 1893. And Mach posed that as a question. Mach has this beautiful book about theoretical physics, really the whole knowledge for education purpose, a little bit like the Feynman lecture, the equivalent. And the question is the following. If you have a sprinkler and you naturally operate the sprinkler, it's going to turn the other way, right? This type of sprinkler here. That's an illustration from Mach, actually. What if instead of pushing water, or pushing pressure, you reverse it and you reverse the pressure, you put negative pressure, so you aspirate water, right, the other way. Would it turn the other way, or would it turn the same way, or would it not turn? There's only three things that can happen. And Feynman talked about doing the experiment, and to make more dramatic effect in his book, said that eventually he put so much pressure that the whole thing blew up and he got into trouble, okay? That's his story. So here's the question for you again. audience participation. Who thinks that if I reverse the sprinkler, it will go, let's say, the same way? No take. Oh, one there, very good. Go the other way. Okay, I would not do anything. Very good. We have a little bit of everything. Okay, excellent. Feynman never gave the answer in his book. Okay, we know what happened in the experiment people have talked about, and you can find a lot of discussion about this type of problem. Okay, here is another type of, so the type of question I'm going to be interested in. First, how do we define or measure chirality? I'm going to try to trace back from historical reason, try to trace back when people decided on what left and right would be. But also I want to discuss about how do we assign chirality to an object. Then I want to understand how does a chiral structure would respond to loads. If I load something, just like the previous experiment, just like the sprinkler, which way would it turn, left or right? Here is an even simpler example that goes back to the really beginning of the field of engineering, or mechanics at least. You go back to Hooke. This is from Hooke's book, 1678. Turns out that Hooke did his homework, but he left half of it away. He didn't answer the second part of the question. The homework problem was, what is the deformation of a spring under load? And Hooke discovered that the deformation is linear with the force applies to it, the displacement. Right? But he never answered the second question of the homework part, which was, which way would it turn? So if I put weight on this little plate, would it turn left, right? Or let's say, would it wind or unwind, or does neither? Okay, so who thinks the spring would wind, so it would get tighter? Nobody? Okay. Who thinks the spring would unwind? Very good. And who thinks the spring would do nothing, just extend, so no rotation? No takers. Okay, very good, very good. I'm accumulating my statistics here. So we really want to know about that, right? If we don't know that, we don't know anything about mechanics or chirality or anything. So we'll try to answer that question, and I'll show you why this type of question is important. So now if I can do the same type of experiment, if I take a chain like that, a chiral chain, and twist it, I can pull on it, and I want to know what happens to it. And why is that so important? Because any kind of stress applied at a given scale would induce a twist or torsion or change of configuration that's going to be mirror in the next scale, or change the type of things that you'll find in the next scale. Same problem with plant cells. If I have, let's say, a fiber-reinforced cylinder, and I increase its pressure or pull on it, would it turn left, right, or nothing? Okay, so that's another question that I want to know about. So basic second question, how does a chiral structure respond to loads? Third question, I want to know how chirality is transferred from one scale to the other one. If you think about it, this is really the simplest question you can ask about a multi-scale problem. You have a symmetry at a given level, a given scale. How is that going to be reflected to the next scale? Right? It's basically a binary problem. If it's left at that scale, is it going to be left at the next scale? Before we do any more complicated theory of a multi-scale problem, maybe we should start with this one. Okay, so first type of problem, I want to define and measure chirality. So we decided that we define this to be left and right, which is important to put the picture. As I said, there is no other way besides doing weak beta decay experiment on cobalt-60 to differentiate left and right than either showing a picture or making a reference to your body or a common object. Right? If you think a little bit, it seems a little strange, but it's a theorem. In free space, there is no proper way to define it without showing it or making reference to an object around you. So suppose that I know that, and now I look at these. Okay, it's a potato, not exactly the same one. Is this potato more like a chiral object or achiral? Is it left or right-handed? Most likely, most potatoes are going to be chiral. But can I assign a chirality to that? This is quite a difficult question. In what sense? What do I mean by that? So I start with a simpler one. So let's take a curve like this one that I 3D printed. And I want to know, or the other one like that, is it left or right? Can I assign chirality to a curve if I know this is left or right chiral? Okay, we're going to come back to that in a second. Let's go back to the convention, left and right convention. And let's start with another great philosopher, Karl Marx, who said, definition is lacking. Who shall define, who shall determine which is the right and which the left? You know, the entire history of civilization of the 20th century might have been very different if he had stuck to this type of question. Here is a young Karl Marx, you know, doing undergraduate studies in philosophy and asking this question. But the same question was asked by another great name of the 20th or the 19th century, which is Maxwell. And Maxwell was very concerned about this problem. And in 1871, he gathered the important scientists at the time, people like Kelvin, to the London Mathematical Society. And he writes at that time, we have the proceeding published in an obscure journal called Nature at the time. He says, in pure mathematics, little inconvenience fell from the want of uniformity. So mathematicians don't care about that. But in astronomy, electromagnetism, and all physical science, it is of the greatest importance that one or the other system should be specified. He said, I don't care what we choose, but we have to choose something. Otherwise, we're going to get in trouble when we talk and we present some results. And so they had this long discussion, and the end of the proceedings, the end of the letter says the following. In consequence, the right-handed system, symbolized by a corkscrew or the tendril of the vine, was adopted by the society. So that's the definition of Maxwell. He says, if you want to know what right is, go to your kitchen, find a corkscrew, and that's a right-handed helix. Right? Very pragmatic, very practical. It's funny that at the time, if you read a mathematical textbook like Tate and Thomson on quaternion or Hamilton on quaternion, they try also to define the same notion. And they realize quickly they can't, and they make very convoluted argument. Because for a mathematician, the idea of referring to a corkscrew, you can think about it. This is not acceptable, right? Everything has to be well-defined proper. But there is no way to define it without self-reference. So they turn about looking at the page, rotating T's, and all that, very confusing. At least Maxwell was very clear. Now, this is right, okay. And in maybe one of the greatest treatises, scientific treatises of all time, the treatise of electricity and magnetism of Maxwell, where he defined the theory of electromagnetism, you find in a footnote, page 8 or something like that, he says, again, Professor Miller suggested to me that as the tendril of the vine are right-handed screws and toes of the hop left-handed, the two systems might be called toes of the vine and the hop respectively. The system of the vine which we adopt is that of Linnaeus and of screwmaker in all civilized countries except Japan. So let's try to unpack that statement by Maxwell. It's all in the footnote always, right? So the tendril of the vine are right-handed screws and toes of the hop left-handed. So vine is what you make with wine, hop is what you use for beer. So you define the word for like people in beer and white wine. Okay, we're going to come back to that because that's a little strange to me. Okay, then he talks of screw makers, and indeed, most screws are right-handed. Sometimes you find left-handed screws. I couldn't find in all these years, in the last 20 years, I've tried, any indication that they had left-handed screws in Japan. I find that Eskimos had left-handed screws, though, the way they make it. So that's a different story. But there's no indication about Japan. So he says we should really use the convention of Linnaeus, which is a great idea because Linnaeus is the grandfather of all convention. He named most of the plants and most of the species. So here is a man that knows about convention. Right? And he says, let's look at tendrils. So I found that very strange because by that time I already worked plenty on tendrils. And if I know one thing about tendrils is that the handedness, left or right, is not well defined. And if you go into Linnaeus, this is a picture from Linnaeus, from Philosophia Botanica, you'll see this is the only picture of a tendril in there. And what you'll see is right and left. So what was Maxwell thinking about when he was talking about the tendrils of the vine? What he was thinking about was not the tendrils, which are modified leaf, but the stem of the vine and the way it twines around its support, right? So it's an error in language, but if you try to define something or reach a convention, maybe you get the right object in the first place. So what about the vines of the tendril? Why are they both left and right-handed? Where Darwin, with his son Darwin also, worked plenty of that. In 1875, they wrote a beautiful book on climbing plants. And one of the things they talk about is the tendrils of the vine, and they always notice that inversion, which I call perversion for a reason you'll find. And the mechanical reason for the existence of teeth is now well understood. The idea is that growth induces an intrinsic curvature in teeth structure. And if the tendril is in tension and rotation is prohibited, there is a mechanical instability that does not favor any particular handedness, and so they always appear both left-handed and right-handed. So if you increase curvature or reduce tension, you create an instability. And why do I call this perversion? Again, I turn to Maxwell, who says the operation for passing from one of the systems to the other one, from left to right, is called by listing perversion. The reflection of an object in a mirror image is a perverted image of the object. Listing was a topologist, who was a mathematician, who called the word topology when he was describing the shape of plant cell. That's the word that's been used, and he's the one who defined his notion of inversion. But let's go back to tendrils. So the way the tendrils are formed is that either by decrease in tension or increase in intrinsic curvature. Here I give you an example. So you start with teeth, for instance. So here's something that naturally curved that I can stabilize by increasing tension. And if I decrease tension, I create a left-handed and right-handed structure with that little perversion in between, that inversion. So I will always have that on my system. So let's look at what Linnaeus said about right and left-handed. So here's the third edition of Linnaeus in 1751 of Philosophia Botanica. And there, he defines what's left and right, and he's completely right. See that little moon that I show you about sinistrosum and dextrosum? Well, he says here is humulus, lupulus. So humulus, that's hop. And if you look, now that we have defined it, this is a left-handed structure, right? And here is bindweed, convolvulus, which is also very common, and that goes as a right-handed. Okay, so at least Linnaeus was right. And indeed, if you go to page 103, again, it talks about both humulus and convolvulus, left and right. No problem. So you think that the debate would be settled. And Maxwell was completely right in giving Linnaeus, pushing the convention to Linnaeus. Here is the problem. In the same third edition, there was an erratum. And the erratum says, on page 103, when you read sinistrosum, you should really read dextrosum. But it doesn't say anything about page 39. So now we have a bit of a problem, right? Should we follow Linnaeus in his first and second edition and forget about that, or take the third edition and ask the erratum and go along page 109? Okay. And that creates a lot of problem among plant botanists in the whole of 19th century. So depending on the scientists, you would call the same structure that you see there, a left-handed structure for us, either left or right-handed. It depends on the scientists. You find both different schools. And then they go into extreme trouble to try to define what they mean. They said it's left view from outside, or it's right view from inside the plant as it turns, or following the course of the sun. I never understand that. So if I follow the course of the sun, which way would it turn? It depends also, of course, on the hemisphere. Or like the hand of the watch, what we call clockwise. But then you have to say, are you looking from above the plan or below the plan, right? So you have to be careful. So you see, nothing is obvious. That's why I put the picture, because that's the right way to do it, except, of course, that there was a very nice article by Gould, the evolutionary biologist, who showed that all pictures of seashell in the 19th century books were actually inverted, and nobody really realized at the time. So you can't fully trust picture either. So. Okay, now our problem, remember, was to, now that we've defined it, after all this work, we want to understand, measure chirality. Now the problem is the following. We want to give a scalar measure to chirality by giving a number to a structure. Here is a curve that goes from a right-handed at the top to a left-handed at the bottom. So if I take pieces of that, it's only going to look completely right-handed at the top or completely left-handed at the bottom, right? So in principle, I can define a scalar measure, parameter chi, that would be +1 there, -1 there. The only problem is that if I want a measure of chirality that's continuous, it's going to cross the axis at some point, and at this point, I'll have 0 chirality, despite the fact that all sections of this curve are actually chiral. So I would have a problem, and it's not a very good fine notion of chirality. So the way to look at it is to go back to mechanics, the help of mechanics, in order to measure chirality. And in order to do that, suppose that I have an object like this one, and I put it in a flow. Suppose that is a viscous flow, for instance, for which Stokesian hydrodynamics would hold. All you really need to assume is that the force exerted at one point is linear in the velocity of the field. So I apply a uniform field U, and it creates a force, so that force is linear in U, so it's related to U by a second-order tensor, and the value of this parameter depends on the physical problem, but I don't care, I take it between 0 and 1. In the case of Stokesian viscous flow, it's 1/2, and it's been studied extensively by people like Howard Brennan. Now, it also creates a torque, and that torque I can also rewrite with respect to any given point R0 as a tensor Q0, right? So I have a force and a torque acting on it. So if I integrate this tensor, Q0, I obtain an object that measures the amount of rotation for a given flow, if I fix the center of mass, for instance, right? So then I can choose R0. I can always choose R0 so that this object is symmetric. That's called the center of moment. There's a distinguished point in probably close to the center where the moment tensor Q0 becomes symmetric, the integrated one. So this object is symmetric, traceless, and change sign mirror transformation. So it's what people in physics call a pseudotensor, that property of changing sign. So it's a good object for us because we know it will change all its value. It's a symmetric tensor, so its eigenvalues are real. But interestingly enough, due to the property of this system, it's always traceless. That means that if you have 2 positive eigenvalues, you must have a negative eigenvalue to balance it. That means that if this object, if I find 2 directions, U1 and U2 corresponding to the positive eigenvalues, that means this object, if I hold it by its center of mass, would always rotate, let's say, right-handed in the same way, clockwise, one way or the other, it doesn't matter, right? It would always rotate the same way. But that means there is always a third direction of which it will rotate the other way. So chirality of the motion really depends on the way you look at the object or the direction in which you impose the field. So you can define, for instance, chirality by the number of positive eigenvalues in this case. Right? In this case, I just computed for you. And just in case you want to know, I computed also this one for this one. So you think you have a good object for measuring chirality, but the same problem of chirality connectedness that I had with a single scalar is still there. Maybe there is a curve that I can choose for which all the eigenvalue would be 0 and would still be a chiral object. And how do we know such objects exist? Because we use them. For instance, if I take an anemometer, if I put it in the wind, it's going to turn a certain way, right? If I reverse the field, if I reverse the wind direction, it would still turn the other way. So in this case, the second-order tensor that I would have would vanish identically, and I really need to go to third, fourth-order tensor. So chirality, in this case, should be seen as an infinite sum of all chirality tensors of increasing order. Okay, so now we have a way to measure chirality. Good, we're making good progress. Now I want to pull on the spring and decide whether it's going to wind or unwind. We go back to Hooke's problem. So I want to understand chirality in a deformation. Why is that important? Well, there is a very nice experiment done on DNA, single molecule DNA, where you can attach a bead, like right here, you attach at the top a bead, and then you can pull the bead and measure the rotation of the object. And when they did this in this Nature paper from 2006, you see the last author is Nick Cozzarelli, the same one who has a prize named after him at the National Academy now. So when they did that, they observed something extremely strange. And we're getting to the answer that the first answer of the day for this little quiz. They look at it and they say, simple physical intuition predict that DNA should unwind under tension, for which we had a majority opinion. But DNA is completely different. We show that for small deformation, contrary to intuition, DNA overwinds under tension. So it says, here is a special object. It's a nano object. It's different than anything we know. It's not like a spring at all. The only problem, of course, is that if you take a spring and add weight on it, you can actually do this computation. This computation comes from the formula of Tate and Thompson in a treatise on natural philosophy. They say if I put a wrench on a spring, what are the rotation and the extension of the spring? And what they show, which is easy to redo, is that for all typical spring, you would always have first a winding and then an unwinding. So you were all correct. That's how we build confidence in here. But people who say that it would first wind are correct. People who say it unwind, it's all a matter of how much you put. And it has to invert at some point. So even the people nobody said that it wouldn't wind, but there was also a possible answer. And the same is true for DNA. So contrarily to our intuition, DNA is exactly like a spring, follow exactly the same law. And with John Maddox, who is at the EPFL, we show that all uniform, inextensible, and shearable constitutively isotropic material rod will first overwind when pulled from their interest state and then unwind. So it's a completely generic property. I'm running a little bit of a time. I've told too many good stories, so I'm going to jump on these. We generalize the problem. What I want you to realize, forget about the picture, is that you can write a simple form of the energy where zeta is the extension and theta is the rotation. And the main thing is that the winding or the unwinding is the fact that there is a coupling between extension and rotation. And that's in that little box. And that coupling is quite important. And that means that whenever you have a spring, you would always have that coupling if B is different from 0. In nonlinear deformation, B change sign. That's the main thing to realize. That's what we know from large deformation. The coefficient actually depend on the applied stresses. So that's a problem, right? If you want to make a spring, a simple spring to measure, let's say, a weight, you will always have that annoying rotation. Okay. Except if you take two springs and put them together, one left-handed and right-handed, and then pull on them, because then the two rotations balance each other. So that's one way to make a spring. It's actually make a much better spring than a helix that would block itself due to the rotation. Turns out that you can also make a much better spring, but instead of taking one rod, you take two rods and put them together. So you take two rods with intrinsic curvature and you put little rigid rod in between. So you force the distance between the two. So that's an interesting structure that you can create. It's something that I did with my postdoc with no faculty in Brussels, Thomas Lessine, a few years ago. So the property of this is very nice. It's exactly like what you expect now. If you do a pure force, if you apply a pure force, you just a simple rotation, always. So it's no inversion in this case. If you apply a pure torque, it will always decrease. So now the system is very simple. But if you have a perversion in the system connecting this right-handed ladder to a left-handed ladder, now this is much interesting because a pure force, there is no rotation at all. It's exactly balanced. And if you have a pure torque, there is no extension at all. So you can fully, with this device, you can fully decouple rotation from extension. This idea of having two rods connected to each other is also related to the problem, an interesting chiral problem that comes in nature. So there are, within the phylum mollusk, there are two classes that are major classes with multiple species. There is the gastropod that you see on the left. So these are all the seashell and snail and things like that that you know, that we see on the beach. And then there are the cephalopods that are mostly extinct. Most species, these are all the ammonites that look something like that, that you see that have no extinct. They disappear, most cephalopods disappear 60 million years ago during the Great Extinction. So these groups are not related at all. They diverged 420 million years ago. So we're more related to goldfish than these two classes of organisms. The interesting thing is that most gastropods are chiral. For a given species, you always find, almost always find the same one. For instance, right-handed is prominent. Sometimes you find an inverted one that's called a perversion, for perversion. And that's the collector really liked these. These have great values, of course. The only one, the main cephalopod that we know is the nautilus, and they're very mostly planar, so very achiral. They have that rotation. So one of the questions we had is, why is one type and one the other one? It's even more interesting by that it's mostly achiral, but there are exceptions. There are so-called heteromorph ammonite that have a well-defined handedness that look very much like seashell, even though they have nothing to do. There is 1% out of the 3,000 genera of cephalopods that have these left and right-handed solution. But they come 50-50%, right? So the gastropods are always either left-handed or right-handed, almost 99.99%. The ammonite that have a defined handedness comes 50-50, almost always. So this is a bit of a puzzle for us. And what we wanted to understand was what is the difference. So the idea was that within the mollusk, you have the animal itself that creates its shell that grows at different rates. And we represented that, I'm not going to the detail of the biology of mollusks, by two rods that are growing within the shell that they build. And the green arrow shows the accretion at the basis of the shell. So there are two main assumptions that we can have. Either the body twists as it grows, or it doesn't twist. And that's the main difference between the gastropod and cephalopod. So in the model, we look at a ventral and dorsal part as growing rods, and that are constrained by the geometry that they build, the shell themselves. And we also assume that they're locally self-similar, and that's the main difference between cephalopod and gastropod, between the body twist. So within that class, there are three types of big solutions that you can have. If you remove the shell, you can assume that the growing rod would either grow without twist, in this case, or with constant twist, and in that case, they would create a helicospiral, a logarithmic spiral shell, or with an oscillatory twist with a periodic oscillation. And then they create these what we call meandering shells. So that's in the absence of the shell itself, is that you assume this is how the body would naturally grow in the absence of its shell, if we remove it from its shell. But of course, it's in its shell, so now it's constrained during growth. And you can either assume no twist, or meandering. So you find the energy minimizer of this solution as it grows, constrained in this cylindrical structure. And what you find is that with body twist, you almost always find the same solution. So you always, if the body twists and builds its shell at the same time, you will always find the same handedness. And that's the basic idea, the so-called Curie principle, that says only asymmetry can beget asymmetry. If you see an asymmetry at a certain level, it's really due to an asymmetry at a lower level. Now, without body twist and low compression, what you find is that the solution is almost always planar. This is really the case of the ammonite. So you'll just have created a nice planar achiral shell. However, if you add higher compression, you have two rods growing in a cylinder, and what you can show is that you have a mechanical instability where you minimize the energy by either twisting left or right, and that minimizes the energy of the entire system. And in that case, you find solution with the same probability being left-handed and right-handed, and this is how you create such structure. And heteromorph ammonite as such that even during the growth of the ammonite, you have different type of shell on the same structure, different type of handedness. So it can be left-handed or right-handed or no-handedness, depending on the development, because different parts of the soft body grow at different rates according to this. Now let me get quickly to the last part on transfer of chirality. Now we understand a little bit deformation and all that. So what we want to understand is how do we actually create this structure? So you can see it in plants. You can see in vine, for instance, who does this motion called circumnutation, which is a word introduced by Darwin to describe this. He believed that he was actually wrong in that, but he believed that most plant motion was were related to this rotation. Or we can look at also octopus arms or elephant trunks, for instance. And the structure is such that if you look inside at different level, you see that these are mostly fiber-reinforced material one way or the other, which brought Joseph Needham, a well-known biochemist, to say that it's not biology as a whole, very largely the exploration of fiber properties. I think many biologists would disagree with that, but if we think about mechanical biology, it's a good guide, that the shape that are formed are probably due to some kind of balance and activity at the level of fibers. In the case of an octopus arm, it's very interesting because it's different rings that have different type of fiber geometry. Some are straight, some are radial, so like hoop, and some are helical. And so it's a type of structure that has different rings with different properties that manage to perform all this motion. And that should be a guide for us. We want also to control chirality, right? If we do, for instance, if you take liquid crystal elastomer, we want to be able to actuate them. These are one that these are elastomeric material that has photoisomerizing molecule within them, and so they respond to line. If you shine a line, they develop curvature. Now, if the light turn, you'll see that the structure, this little pillar, turn also. Okay, so it's a one way to create torsion. It's a very strange way when you think because it doesn't twist at all. It can keep turning as long as you want. There is no twist in the system. So liquid crystal elastomer are very interesting for many reasons, for actuation and other problems. So the general problem is that it's easy, or say there are plenty of ways we can create curvature in device or activation or in nature, right? For instance, if we have two metal and they have different expansion coefficient, then an increase in temperature, they have different lengths. But if they are forced to be together, it would create curvature, as we know from the work of Timoshenko and bimetallic strips, right? But the real problem, which is much more difficult, is in 3D. How do you actually create twist or torsion, right? So if we go back to the problem of curvature, we have this relation between the curvature and the torsion that I told you about. There are more ways, but there are essentially two ways to create torsion. One, you can have fibers that are straight and create curvature in different direction at different level. So you say two units, one bend one way and the other one wants curved the other way. And together that create torsion, right? So you create curvature, but the direction in which you create curvature change along the axis. And that would naturally create torsion. And that's by changing this coefficient phi, having a constant phi, the direction of curvature change as I go along the axis. Or the other way is to have fibers that are helically oriented. So you can take this device and twist it, and all the fibers are helically oriented. And now if these fibers get activated, shorter or longer, then you create stresses in the system that's going to be relieved by an overall twist in the system. That's not enough to create torsion, but as soon as you have twist plus curvature, that's torsion. That's what the last equality tells you. If you have twist, if you have U3 and phi s at the same time, then you create torsion. You need both at the same time. So the general problem, now zooming again out, is if I know in my material, in a three-dimensional material, if I have embedded fibers, let's say mostly a cylindrical geometry, that I can activate or grow, which is the same problem mechanically, at each point in the section, or do I go from this knowledge of what happens in the section, in the microstructure, to the overall curvature, so the curvature and the stiffness of material. So it's really a basic problem of upscaling. So I'm running out of time, so I'm not going to give you how exactly we did the mathematics associated with that. I'm going to zoom quickly, so ignore these. It's very nice, just want to say that. But I realized weeks ago that I had way too many stories about chirality that I wanted to tell, and I wouldn't have time. But the main message is the following. Here is an interesting case of fiber activation. You can think, for instance, of a cylindrical type system where you have this helical fiber going around, and you can activate them, so you can make them longer or shorter, right? And what you want to know out of that, if I can control this, or the biology controls it, or is it going to affect the overall shape? And that's now a problem that we can fully solve with this equation, but I don't want to go through equation. Let's go into the picture. So the basic thing is the following. If I give you within a three-dimensional cylindrical material, or each element grows at each point, I can essentially average over the cross-section and give you the intrinsic shape that it creates in three-dimension view from a great distance. So the knowledge of the change in the microstructure, such activation or growth, allows me to directly relate that to the overall system. I have a nice formula that connects all that. So I can do that explicitly. And for instance, we've looked at, in the case of tropism in general, we have a general theory for tropism that tells you, for instance, that how a plant would follow the course of the sun, left or right, I don't know, but it does follow the sun, for instance. And the idea is that the information is carried from the tip of the plant all the way to the side by a change in auxin concentration, which induce locally change of curvature, and that's what creates the overall torsion of the plant. I can do the same with liquid crystal elastomer, which is a very interesting problem, because now I have to look at how light comes in my material as it deforms and integrate that in order to find the curvature. And doing that, we found that depending on the length, oops, let me go back there. Depending on the length, my material would curve and eventually would reach a certain critical length at which it would go flat, exactly like you see in the experiment. So we can go from the external stimuli, in this case the light, to the shape and have these curvature that are created by this problem. Now, going back to Darwin and the problem of circumnutation, this is a system where instead of having fibers that are straight and change the curvature, the fibers are actually oriented helically and create, through a wave of auxin going in the plant, overall twist and torsion. So this is the circumnutation. The plant is looking for support because it cannot self-support it. And once it finds it, it starts twining around the post, you see. And this is the same version of the problem. You both have growth, you have gravity, you have contact, and you have torsion along a pole. Now, that's all well. You see that, and you can reproduce and simulate. But again, from an engineering perspective, how do you control that? What would be a simple design that you could use to harness this type of structure? It's not biomimetic, but we still can learn something from the octopus arm and having these different ideas of concentric ring having different type of activation. For instance, you can think of the red rods within the section as being able, that are straight and being able to activate growth, so just extend or shrink, and the one in the green twisted helically around it. And the question is what type of structure we can create with that. Here is a simpler design where each rings as each cross-section, you have the red zone where you can activate by a constant or by whatever amount you want along the ring. And what we found is that independently of the number of rings, each ring is controlled by 3 independent parameters. Actually, the integral, if I know the growth or the activation in each ring as a function of the angle, So it doesn't depend on the radius. The dependence on the radius is constant in each ring. Then I can identify 3 parameters that tells me exactly the curvature and the torsion. Now, this is going to be one of my last slides. You can now design with a given function. For instance, if I have a structure like this one, which is a cylinder with three activators in green, and when I activate that, they extend, and I can choose the extension, I can try to design it. I can try to find the activation necessary, for instance, for a simple task, like going to the target endpoint. So the only thing that happens in material is that the green part gets uniformly longer or shorter, just depending on its activation. Here is a more complicated task. You want to go to the target endpoint and avoid the object, or in this case, a cylinder. And here is another design just by changing the chirality of the external rod. And a 2-cylinder design is actually much better. The only thing you can do with a 1-cylinder design, a 1-ring design, is create a helix. You can actually show that's the only possible structure. So it's very limited. But as soon as you have 2 or 3, now you can create much more complex tasks in terms of soft robotics, if you want. So this is joint work with Alain Goriely and a student, Bartek, that we've done recently. Okay, I'm getting a little bit out of time, so let me conclude. As you see, the history of chirality is important in many different contexts. It's a history of confusion, which is not very surprising. And chirality measure is important in many aspects. And what you see is that geometry by itself is not enough to understand chirality. If you take ideas from mechanics, such as material properties or material symmetry and stresses and things like that, you can learn a lot more about chirality. Now, understanding mechanical chirality is surprisingly counterintuitive. And again, we can do this last test for you if you want, since you love my little quiz. Here is a fiber-reinforced cylinder with helical fibers. And I extend it or put it under pressure, if you want, internal pressure. Is it going to turn left, right, or not at all? So is it going to unwind or wind? So who thinks it's going to unwind, the helical fiber going? I've lost you all. Who thinks it's going to wind as I increase the? Who thinks it's going to do neither? Excellent. Thank you for playing. Okay, and as I told you, if you see the literature now, even simpler problem like the problem of DNA, there is quite a bit of confusion about how this chiral structure behave. The main point is that mechanical force, material symmetry, and geometry, just like for the definition of measure, are important. Now, transfer of chirality and inversion of chirality is also very interesting. And again, what you learn is that there are multiple sources of chirality. There's not just one. If it's left at one scale, it's going to be left at the other scale. You really have to understand the mechanics and how stress and relief in the construction of the structure at different levels. You really have to integrate the whole thing in order to understand how it works. You have this nice inversion that I created through instability. The case of heteromorph cephalopod is a compression-driven instability. The case of tendril perversion is curvature-driven. There is another set of problems related to fungi, the Phaeomyces, where you have twist-driven instability. And I'm going to leave the last very final word to Darcy Thompson, who has been a great guide and motivation for many people studying morphogenesis. And he looked at the problem of seashell in particular, and in his book on growth and form, he writes, but why in the general run of shell all the worlds ever, in the past and the present, one direction of twist is so overwhelmingly commoner than the other? No man knows. And I'm gonna stop there. Thank you very much.
Any questions? Thank you for that fantastic talk.
It seemed like when you were defining the chi parameter, the chirality seemed to be like a local measure. But when you were talking about the integral with the Q, like it seemed like more like a global measure, so and that's where it seemed like the chi equal to 0 transition.
No, yeah, I wasn't clear. The chi equals 0, for instance, is the integrated torsion over a segment over the full curve, right? So that's also global. Now, we know in fluid mechanics there are local notions like elasticity and chirality that also carry the same information, and that you can also integrate to the whole system. But yes, what you really want would be to associate to the whole body a notion of chirality.
In your definition of mechanical chirality, I think implicitly you've assumed that it's
Is it or not? Can you try the other?
I can hear you.
Oh, okay.
I can repeat it. Okay, go ahead.
Sorry. So in your definition of mechanical chirality, I think implicitly you've assumed isotropic material parameters in defining these sort of characteristics of the moment tensors. Have you encountered in nature an example of something that is perhaps geometrically chiral in one way, but perhaps is so anisotropic in its material parameters that you would define it as mechanically chiral the other way?
Yeah, that's a great question. I didn't have time to go. So parity in physics, chirality in chemistry, what is the equivalent for us in mechanical engineering? It's really asymmetry in material group, symmetry group of the material. So in principle, you could have at the local, at the pointwise level, a material that when you pull twists, you can have this coupling. It's not very hard to imagine, and it's quite easy to realize for some system. In this case, the material property, the local material property would have an effect on the overall system. So this is what actually happened for twining plants. You can imagine that one little cell, because of its internal structure, when it's subject to change in turgor pressure, extend and twist. And that's the third type of way you can create torsion without that is different than the other two. I said that you can locally change curvature in different direction. You can have helical fibers that are also straight. You could also have the third one, which is suppose that all the fibers are along the axis. But each fiber at the local level, when you pull on it, induces a twist. And in this case, you would have exactly the situation that you have. The asymmetry would not be related to the geometry of the fiber or the geometry of the object, but by the symmetry group of the material. Locally, it would induce that. And that's yet another possibility, which is also very interesting, because if you think about a liquid crystal elastomer, most of these are chiral structures, so as they extend, you can have these type of properties, right?
From one scale to the other, what is the role of residual stresses that you generate at once?
Excellent question. So I said, what did I say? Geometry of the object, probably chirality. I said that geometry of the fibers, more at a little scale, or symmetry of the material. And then there is the fourth one, which is chirality of the stress itself. That can be induced by residual stress, for instance. I have a nice example about that also induced, which automatically suggests another problem. We can define chirality for a vector field. That was well done in fluid mechanics, the notion. You take V times curl V, right? What is the notion of chirality of a tensor field? I don't have a good answer. It could look like that, but does it have the right properties for that? And that's what we need in order to understand how it would go to the next scale. I'm surprised that nobody wants to know the answer to these problems. So you're all going to go home and you'll never know which way turns which way. Not this one. That's the great question nobody knows, right? See, I like the fact that it's a bit of mystery. Why do we have seashell? Oh, why? I don't know that. I don't have any answer. I think it's best left unanswered. Okay, I do have. There's things that I know now that Darcy Thompson didn't know about seashell and the way they build. it turns out that chirality of the soft body of the gastropod is induced in the division from 2 cells to 4 cells. Already, there is a cleavage plane within the cell that induces an overall helicity. So when it goes, you already see a difference. It turns one way or the other one at that stage. And when we go to 4 to 8, it already built a little helix. Right at that level of cellular division, going from 2 cells to 4 cells, really early, very super early in development. So why is there one hand versus another one? The why and therefore, well, you wouldn't write no man knows, but I would say no one knows these days.
One last question.
I can show. So in rubber elasticity, if you twist the rubber, you're going to have a pointing effect where you have to expand it, otherwise you have to compress it, otherwise it's going to expand. Yeah. So then my question is, can you use this? This is a boundary value. This is a boundary condition for the nonlinear material property. Can you use this to create some interesting actuation pathway or?
No, just the pointing effect itself. Usually you want to avoid it. So you avoid the pointing effect in transmission in the torsion of a cylinder, because then in an engine or so it gets a little longer or shorter, and you want to avoid that. Is there any interesting, I mean, there are interesting coupling that occurs there, but can it be used for something? I don't know, maybe. I don't know. I'm not that creative yet. Yeah.
Is there any relationship between how the earth turns, gravity, and all that?
Or gravity plays a role, or Coriolis force, things like that? Yes. So if you do the computation in plants, for twining plants, you realize that the Coriolis force is proportional to the velocity of the object. So plants are going quite slowly, right? And so if you look at the force that it will induce, you realize that the force of Jupiter is higher than the force of Coriolis force. So you're more likely to believe in astrology, the effect of planets, than the effect of Coriolis force. It's completely negligible at that time. But maybe, since nobody asked the question, okay, that's for the cylinder, so we can go back to that. What about this one that was done here in the first place? So if we believe Coriolis force, if you look at the way a hurricane moves around, you'll conclude that it should go counterclockwise in this hemisphere, right? But if you actually do the experiment, is that right? Because I guess the velocity is extremely small. We're not talking about the size. While Shapiro did the experiment and removed almost all possible disturbance. And that was very hard. So he did a big tank, and he had a long tube so that it wouldn't, when he opens, he removed the tap, it wouldn't induce vorticity. And then he had to wait 2 days so that the residual vorticity within the tank dissipates. And then open it, and then he saw the systematic counterclockwise. And then Trefethen, a few years later, when he went on sabbatical in Australia, repeated the experiment. He knew the experiment from Shapiro and saw the clockwise motion. In Shapiro's paper, he said, oh, it would be a good idea to do the experiment in the southern hemisphere, which Trefethen did. And I had a chat with Nick Trefethen, his son, about it, and he went with his father. He was like 10 at the time, and he had the pleasure of pulling at the end of the tube and remember very well the experiment and how it worked. That's right. At the time, it took 28 days to go from Los Angeles to Australia by boat. That's how you people did the sabbatical.